grade 9s, we're going to start a new unit today, space and exploration. We'll go in more detail with everything, but today we're going to start with the distribution of matter in space as well as the composition of matter in space. So does everybody have a mini whiteboard in front of them? Great. Yeah. I'm going to give you about 40 seconds to draw what you think our solar system looks like. And so our solar system, we have 8 planets, we have our sun, and there's other things like asteroids, meteorites. There's no right or wrong answer here. You can get as creative as you like. What does our solar system look like? Maybe another 10 seconds. Wrap up your last idea. All right, can everybody hold up their boards just so I can see that we're all on the same page? We're drawing some sort of solar system. Nice, I like the idea. Does someone want to share their idea of the solar system?
The solar system is...
Can you hold it up so everyone can see?
So
what did you draw?
The solar system is the sun and every planet that orbits around it.
Really great idea. So you have the sun at the center of our solar system.
Yeah.
That's awesome. We're going to get into that model a little bit later. Does anybody have a different idea or a different depiction of our solar system that they want to share? Other than the sun and the planets, did anyone include other bodies, like asteroids or meteorites? What do you have, Josh?
Have a like a meteor belt. The first one.
Nice, the asteroid belt.
Asteroid belt. That's it.
That looks great. Okay, so we're going to talk about 2 different models of our solar system that kind of have developed over history. But first, I want to clarify some terms. So these terms cannot be used interchangeably. They actually explain the scale of things in space. So our solar system is our sun, our planets, and like I said, meteorites and asteroids, anything else flying through it. Larger than that is a galaxy, and our solar system is one of these little specks in what we call our Milky Way galaxy. And then larger than our galaxy are clusters of galaxies. And there's different variations of these clusters, but all you need to know that clusters like our Milky Way, galaxies like our Milky Way, cluster in larger groups. And then all these clusters together is what makes up our universe. Now, we don't have actual pictures of our universe. This is kind of an artistic interpretation, but it just gives you an idea of that scale and size of the terms that we're going to be using throughout this unit. Okay, so now we're going to go back to our models of the solar system. So way back in the day, a guy named Aristotle came up with this model called a geocentric model. So I'm going to hand out some worksheets here really quick. See you guys?
Thank you.
Okay. And just a reminder on your worksheet, anything that's highlighted on this PowerPoint, you can fill in on the worksheet, and you have some diagrams to reference as well. So our geocentric model was proposed by a guy named Aristotle, and he put the Earth at the center of our solar system. So going back far enough, they didn't have the same technologies that we have today. So the best scientific tool that people had was their own observations and experiences. So if you were standing just outside and you saw the sun going across the sky east to west every day, you would assume that that sun's going around you. So it's natural to think that Aristotle thought the Earth was at the center of our solar system. However, there was this other guy named Copernicus, and he actually didn't agree with that, and he proposed that the sun was at the center of our solar system. And this is what we call a heliocentric model. Okay? So these were the 2 ideas of the time, and they were conflicting ideas. Neither one had solid proof because, like I said, the technology of the time was mostly observation and experiences. However, about 100 years later, Galileo came around, and he, using the first telescope of his day, which is about as strong as a normal pair of binoculars that we have, was able to observe phases of a planet named Venus. And when he observed the planet's phases and its pattern, The only way that these phases could happen was if you had a model with the sun at the center. So Galileo gave us our first bit of proof that the sun was at the center of our solar system. So our solar system is a heliocentric model, not a geocentric model. All right, so at the center of our solar system is the sun, and we have all our planets wrapping around it. Does anyone have some ideas about why planets orbit around the sun in the first place?
Gravity.
Gravity. Thank you. That's awesome. Yeah. So everything that has a mass in space has a gravitational force or a gravitational attraction. And the larger that mass gets, the stronger that gravitational attraction becomes. So our sun in our solar system is massive compared to the planets. So it has its strongest gravitational pull. And that's why the planets naturally go around it. Now, there's 4 types of orbital patterns. Next slide, please. So you don't need to write all these definitions down. You have access to the PowerPoint, but you need to know which orbital pattern our planets follow. But the first one we're going to cover is a spiral orbit. And so this is when an object comes in at a really steep angle, so steep that it essentially crashes right into the sun by doing a tight spiral. Okay? This happens with meteorites, asteroids, that kind of thing. They come in so fast and so steep that it just wraps around the sun and crashes. The next one we have is a hyperbolic orbit. Okay, and you guys can observe these orbits on the diagram on your worksheet. They should all be labeled there. So this is when an object is coming so fast that the gravitational pull of the sun actually can't catch it, or it's so far away that the force isn't strong enough to pull it in. So what it ends up doing, it creates a U shape around our sun, and then it just flies on by and it never comes back into our solar system. That's a hyperbolic orbit. A circular orbit is actually very unique. It's very rare. We don't observe this a lot because you require perfect circular motion. So there can't be any eccentricity, which means there can't be any wobble or deviation from that circular pattern. Okay, so we don't see this a lot, but it can happen. Our planets are actually very close to a circular orbit, but they're not quite there. So our last orbit is our elliptical orbit, and this is what our planets follow. So an elliptical is essentially an elongated circle or an oval. If you see on your diagram, that's the shape that it has. All right, so in our solar system, we've talked about the sun being at the center, and we have our planets orbiting around it. But what about all that extra space? Well, it's not just an empty space. There's actually things called dark energy and dark matter. I'm not going to go into too much detail because I'm not an astrophysicist, but all normal matter, which is things we observe and that we are familiar with, like rocks, minerals, planets, the sun, only makes up for 5% of the entire universe. Everything else is made up of dark energy and dark matter. Dark energy, we can, in a nutshell, be explained as the force that causes the expansion of our universe. And dark matter interacts with other matter through gravitational force. That's kind of all you need to know about that. Okay, so now that we have the basic idea of where things kind of land within our own solar system, we're going to do a little bit of a demo to show how things interact in our solar system and space. So if I could have everybody kind of come around our demo here. Yeah, you guys can just make a circle. All right. So this is space. Okay. So if this is like a space-time continuum, these marbles that I have here and rocks represent matter in space. So we have a larger object. This can kind of be our sun. You can see that space bends, and that represents the gravitational pull that it has. Okay. So the larger an object, the larger that gravitational force is that we were talking about, so the more space bends, okay? Smaller objects, maybe something like our Earth, still has a mass, so it still bends space, but not as much, okay? So if we have our sun in the middle, and I have a smaller object, and I give it a force sideways, what do you think is going to happen? Yeah, it might go around in circles and end up in the middle. Let's just test it out. All right. So it eventually kind of took a more of an oval shape at the end, our elliptical. Did spiral to the middle because we're not actually in space. But that represents the orbits of our planet. We'll do it again. Okay. So who can remind me what happens when two objects are close to each other because they each have a gravitational pull? What do you think is going to happen when they're both put in space? Yeah, they're going to be attracted to each other. Let's test it out. Nope. Not quite heavy. Let's try it. No. Pulled space too tight. Okay, so that's all right, but who can maybe explain why they didn't get attracted to each other? What? Exactly. So even though we had two objects and they were still bending space, they just weren't strong enough to bring them to each other. Okay? Something that might be a little bit heavier, they would come towards each other like that. Okay? All right. So what else can we test here? All right. So if we have our sun in the middle, now this one is really tricky to get to work. So we'll see what happens. If we have objects going in different directions, what do you think is going to happen?
They might collide.
Yeah, we might see some collisions. What else is going to happen? Are they still going to orbit, or are they just going to fly off space here? Or what's going to happen?
All gonna end up in the middle.
Might end up in the middle, yeah. Why is that?
Because of the gravity.
Right, we still have our sun in the middle. All right, so let's test it out. All right, what did we observe?
They all went to the middle.
Yeah, they all ended up in the middle.
The ones that were left moving were all going in the same direction.
Perfect, that's what I was looking for here. So, for whatever reason, we don't really have a good explanation for it, but there's a preferential direction for things to be orbiting in space, and it's a clockwise motion. So our demo doesn't always show it, but we got it that time. Try it one more time here. Get it going. Okay. Yeah, so they all ended up in a clockwise motion. So we still have things in our solar system that fly through, like meteorites and asteroids or just other objects, and they're going counterclockwise, but through collisions, they're taken out immediately and they go right to the center where our sun is. What's left over are objects that still move in that clockwise pattern. And that's what we see in our solar system. All the planets move clockwise. So what's going to happen if we have two heavy masses? Like if we have the Earth and the Moon, for example, because who can explain to me what happens between the Earth and the Moon, similar to planets in our solar system?
That's Earth.
The Moon orbits Earth. Can you tell me why?
Because it's small enough. The Earth's pull on the Moon is strong enough to keep it in an orbit as opposed to letting it get away.
Exactly. So just like the sun keeps our planets in an orbit because of its gravitational pull, the Moon stays in orbit around the Earth because of the Earth's gravitational pull. Okay? So let's pretend this is Earth and this is the Moon. So the Moon is going around Earth here. This is our rocket ship. What's going to happen when I give our rocket ship a force is if we're leaving Earth and we're going to go for a moon mission. What's going to happen? It's going to stay in the Moon's orbit? Yeah, that might happen. Yeah. Any other ideas as to what might happen? Is it going to just collide with the Moon and stay over there, or is it going to go in orbit, or what's going to keep going right past.
Depends how fast it's going.
Yeah, it's going to depend on how much force I give our rocket.
Exactly.
All right, let's test it out. See if this one works. All right. This takes a couple tries, so just bear with me here. Come on. All right, one more time. No? Alright. No. Okay. So what you're supposed to see happen is actually our marble make a figure 8. I'll try to couple more times. Our material got stretched out a little bit. Alright, well, oh, there we go. We almost got it, but it's not supposed to fly. Alright, well, at the end of class, I'll let you guys play with this a little bit more, and you can see if you can get a figure 8 going. So our marble is actually supposed to make a figure 8, get caught in the gravitational force of our moon, and whip back around to Earth. Okay, we actually saw that in one of the Apollo missions when they actually put a moon on the moon, and they used the gravitational force of the moon to come back to Earth. So yeah, that's an example of what our space mission has used.
Could there ever be a perpetual orbit like that? Like, there's always planets orbit the sun forever. Could there ever be a figure 8?
Well, that's a really good question. I don't see why it wouldn't be possible. You'd have to. Yeah, that's a really good question. I'd have to look into that one. But the gravitational pull of the moon and Earth is different because they are different sizes, so you'd have to take that into account. Maybe if the two objects had the same mass, you might be able to find that perfect figure 8, but to whip around the Earth would be a lot different of a trajectory than to whip around the moon, right? Because there's different forces. So it might be possible, but we'd have to look into that one. All right, so the last thing I want to show, because we are talking about the moon and the Earth, and our moon orbits the Earth as they both go around the sun, so we'll just demo that here. All right, so can you see the little one kind of going around the larger object? Oops. Yeah, so the little one does orbit the larger object because we are creating that bend in space, and so the smaller object does get caught, and as they go around the larger one. So yeah, and later maybe we'll try out the figure 8 again and see if it works. Yeah, that's our demo.